Hello, this is question 5, part B and C of the extended response. And in a previous section, we defined a function s, and we also found a value of c here as 8. So for this part, we need to find the average rate of change. So that becomes s of the natural log of 8 minus s of 0 over the natural log of 8 minus 0. So I have the function already defined from the previous section, and to work this out, we can punch it right in. So we have the natural log of 8 minus s of 0, which gives -4, divided by the natural log of 8, gives us -4 on 3 times the natural log of 2. And that's our average rate of change. So for this question, we're given a new function, v of t, and this is a more generalized case of the previous function s. You can see here, s has a kind of weighting for each exponential term, has 2 units here and 8 units there, a kind of scale factor. Here it's adjustable depending on the d. And d is a value between 0 and 10, not inclusive. The way I'm going to do this question is I'm going to do it naively by following max-min procedures. Then I'm going to show you the curves on desmos.com. I could show you on the CAS, however, I need to use the sliders, and they've been playing up on the emulator. So I'm going to use the sliders on Desmos to show you how this question actually plays out. So instead of using the sliders on a computer, you'd use the ones on your handheld CAS. So we're looking to find the minimum value of this function. As soon as we see that, we think, right, we need to find the derivative. And we want the minimum value to occur when t is the natural log of 9. And that means that derivative is going to equal 0. And we want to solve for d. We're saying find the value of d such that this minimum occurs when t equals 9. So we can get out our CAS here. The first thing we want to do is actually define that function, v of t. So let's put it right in. So menu 1, we want to define v of t equals, we have d, some variable, times e to the power, d times e to the power of t divided by 3 plus 10 minus d times e to the power of -2 times t on 3. Okay, and we'll check that that's been entered correctly. It has. So we want to take this, we want to find the derivative. So let's define that. We can go and define the derivative. We'll call it dv of t. And we want that to equal the derivative. So we're taking the derivative with respect to t of this function, and we've done that. Now, we need to solve that derivative when t is the natural log of 9 for d. So let's do that. We need to solve that derivative, dv. Now we're taking the natural log of 9 as the argument. So that's our t value. Natural log of 9, we want the derivative to equal 0, and we're solving for d. So we get d equals 20 on 11. Now here it says, find the set of possible values of d so that the minimum value occurs when t equals 0. Here it was when t equals the natural log of 9. Here it was when t equals 0. So the naive approach is to take the derivative once again, this time set t equal to 0, and we want to find d once again, and we can literally just grab this and change that argument for the function to 0. And let's see what we get. 0, we get 20 on 3. So this time we think d equals 20 on 3, and over here, this time we have the same question but t equals 5. So we want to evaluate the derivative when t equals 5. We want to find d. Let's see. We get 20 on e to the 5 plus 2. Now, there's something wrong here. The thing that's wrong is whenever you get a max-min question, you must check your endpoints. And they've given you a hint here. You must check these. They've given you a hint here because they're saying the set of all possible values. That is a set, but it's a very uninteresting set. We want the set of all possible values that give a minimum when t equals 0, and all possible values that give a minimum when t equals 5. So you can set this up on your CAS with sliders to look at this, change the values of d, but I've set it up here in Desmos just because it looks a bit nicer. And also because I can't get sliders working on that emulator. So here we have the function. You can see we have the function defined with the restricted domain. I'm going to get rid of the restricted domain for now. And we have d we can change from 0 to 10. And here are the two values we found. We found the 20 on 3 for t equals 0, and we found this value for t equals 5. So I've got those values here. We have the 20 on 3 here for when t equals 5, and this value here for t equals 0. Let's confirm that's right. No, 20 on 3 is for when t equals 0. This is for when t equals 0. This is t equals 5. And we're playing with this. So let's go to d equals, let's play with this d value. This 20 on 3 here is about 6.6. There we are. You can see what's happening there. See how that minimum is occurring right where we would expect it. It's occurring when t equals 0, which is exactly what we have here. That minimum's occurring when t equals 0. However, it's a local minimum. Just there. It's a local minimum. Same for here. Let's look around 0.13. Let's look at 0.1. So when d is 0.1, we're getting that minimum at t equals 5. However, we have a restricted domain. So let's put in a restricted domain. You can do this on CAS. We have this restricted domain. Now let's play with our slider. See what's happening here. Let's go up to 6.7. So we had that local minimum there. But we can keep going. And we still have that value as the minimum. For all these values of d, that's still the minimum of this function. Without the restricted domain, it's not. But when we put the restricted domain back in, we can see that that's the case. So our naive approach doesn't work. Same for down here. You can see, sure, you have that minimum value just there at that 0.1, at 0.13, but it's also all these values. In fact, we can view them a bit more closely. Let's have a look. There's still these values here. If you look at the graph changing, those are minimums as well. So, how do we actually answer this question? Well, we know from looking at how that curve moved around, if we go back, we have the 20 on 3 here, but we know, looking here, that D doesn't have to be just 20 on 3 or 6.6 something. It can be 6.66 and it can get bigger and bigger. So we have to define a set. So we found this D value, but our final answer will look something like this. We know that D is an element of, it includes 20 on 3 because we saw that that was indeed a minimum, but it also includes everything up to 10, like that. Noticing the curved bracket, we can go all the way up to 10. It's the same for this one. We have D. D can be 0, noticing the curvy bracket there, but it can also go up to 20 over e to the power of 5 plus 2. Remembering that we have a square bracket there because we're including that value. So those two there are your answers, and it's all about watching those endpoints. Very tricky stuff to look out for.